and welcome to the Waste Gas Capture from Abandoned Mines, presented by Brent Bobsein with CNX Resources. Mr. Bobsein is Vice President of Sustainable Development with CNX Resources. He has worked for CNX for 13 years and graduated from Case Western Reserve University in Cleveland, Ohio. Please join me in welcoming him.
Thank you. Hi, everybody. I'm Brent. If you have questions or you want to have a discussion along the way, we've got a nice small group, so please feel free to jump in. I don't have enough content to cover up the entire period of time here, so I'm happy to have discussions as we go. So I'm an engineer by trade, background in mechanical engineering, and after graduating, I got into kind of the natural gas industry, did system design, project management. But over the last 4 years, I've been able to start working on projects like this that capture waste gas, including methane, from abandoned mines, and then converting it into some sort of beneficial end use. So that's something that's been really great for me. It's very exciting, something I'm passionate about, and I'll kind of explain why. So methane is a very potent greenhouse gas. It is one of the leading drivers in contributing to climate change. And so at an international level, there's been a lot of focus on it. Global Methane Pledge, International Energy Agency, United Nations, right? Like they've all got individual commitments that focus on methane because it is a short-term enforcer of greenhouse gases. Over a 15-year period, while it's in the atmosphere, it's almost 100 times more radiative reinforcing than carbon dioxide. So it is something that's kind of seen as the lowest hanging fruit in terms of what we can do to lower climate impact. So how does that tie to mining? So during the mining process, I'm showing a typical longwall mining operation here. So we've got this guy underground, and there's a shield over him, and there are shears cutting the coal seam right here. And in this image, he would be kind of moving in this direction towards us, and then in this direction cutting through this coal. What happens is, as these shears grind this coal, there's methane trapped in that coal seam. Additionally, as this longwall progresses and moves from left to right, the overlying strata fall and collapse behind the shield, and it's roughly that seam height is what all collapses. This fracturing and collapse of overlying strata has a lot of gas in it, whether it be other coal seams or shale deposits. That mechanical fracturing creates a big influx of methane gas that comes from overhead, as well as at the actual face. So this guy's got gas coming at him from two directions, and it's kind of shown in yellow here, how it's coming from this way in and this way in. So that, unfortunately, in the past, has caused a lot of tragedies and explosions, right? So if there's a spark that goes off while this methane is being in this atmosphere, there can be an explosion, right? And that's unfortunately what's been the cause of countless disasters in mining history over the last century. Has anybody heard of the term the canary in the coal mine? Right? So that came from this concept of you had to have some sort of safety prevention system in place, and back 100 years ago they had a bird, and the bird died, then, well, there's too much methane, and here we got to get out, right? That is the precursor to an explosion, and that's why the Mine Safety Health Administration established legal requirements saying these mine operators, they must install degasification systems. They must get this methane out from these underground workings to keep these guys safe underground, preventing a buildup of combustible gas. So the explosive range for methane is around 5 to 15%, and so the methane concentration underground needs to be kept below 5%, and typically they target around 3 just to be safe. So that's the requirement underground. These mine operators must install safety systems to get the methane out from underground to the surface. So how do the mine operators do that? So they do it one of two ways. What I'm showing here is called ventilation air methane, which is a big fan. It's an air duct that basically pushes atmospheric air down and then sweeps across the mine face where these guys underground are standing. So there's basically a tunnel right here that air pushes through, and then it comes and sweeps across where this guy's standing. This is like the side view of that last image that we were looking at. And as you're standing here along the mine face, you can basically feel that wind being swept across. Your pants would be shaken in the wind because there's so much air being pushed across you. That gets diverted up into a stack, and the concentration of this methane is less than 3%, like we talked about. The other degasification method that these operators employ are called degasification boreholes. So we talked about how the overlying collapsing strata was mechanically fracturing and it was releasing all sorts of methane behind the longwall face, behind the shield. Well, these mine operators learned they can install these boreholes here and they can redirect this gas up into the surface rather than it migrating from those collapsed strata to where the mine operators were. So now you've got methane going to the atmosphere and it's not underground, which is good for the underground workers. It's keeping them safe. But what happens to the climate, right? Well, right now, that stuff is just being pushed to the atmosphere. It's being vented. And if you look at historically in the United States, less than 1% of mines do any type of capture for this because it's safety, and it was safety first, and greenhouse gas management has been kind of a recent focus. It wasn't the focus of the 1970s to the 1990s, right? It's a more modern thing. So now when we look at abandoned mines, these mines will continue to vent methane to atmosphere for decades after mining ceases. So we have an operation where we are capturing methane from one of these degasification boreholes that was originally installed by Quaker State, I think in the 1980s, and it's still producing a really large volume of gas today. And there are hundreds of those sources throughout the state of Pennsylvania, and that's what I'm going to talk about a little bit today. Yeah.
How long is a typical long walk?
In width?
Yeah,
Yeah, so that's a good question. I think it's. Yeah. Yeah, I think that makes sense. I've seen 750, and I've seen larger than that. Different, yeah.
Currently, there's no capture of that methane.
So I'll get to the great question. We've got a project that does that, and I'm going to talk a little bit about some of the projects that are doing that. So it's rare, right? But you really set me up for this slide, so thank you. Yes, sir. Go ahead. Yeah, cool.
I want to ask how does the methane underground get stored? How is that released? Is that already stored underground?
Yeah.
And then eventually through the breaking of the rock with mining, it just gets released over time.
Perfect question. Yeah. So there's two sources. Back to this image. There's two sources. This isn't really showing up too well, but the two sources are entrainment in the coal. So every coal seam has a certain standard cubic feet of gas just geologically trapped in that coal per ton. And depending on which coal seam you're targeting and which region of the U.S., each mine is going to have a different standard cubic feet of gas per ton of coal just inherently in the coal. So think about fossil fuels in general, like the age of a fossil fuel determines what compound it is. And at a certain age, it's coal, and then at a certain age, that coal degrades, and maybe you have microbiomes eating complex organic compounds and turning it into methane, right? So just different ages, different geologic conditions form different concentrations of methane. So that's what's happening here, but then overlying strata, you hit it head on, right? Think about like a natural gas well. a natural gas well may be drilled hundreds of feet into the earth, and they may target a certain seam. Well, if that same seam that was being targeted by that natural gas well presides above this coal mine, what's going to happen? That reservoir is basically going to be released from above down into the underground workings. So it's geology, it's gas in place, and it's stimulated reservoir volume. By stimulated reservoir volume, I mean what is unleashed by the mechanical fracturing.
So then I guess the second question is, what else is released besides methane gas?
Yeah. So the other thing that we pick up a lot of is oxygen and nitrogen, and that's mainly because, and carbon dioxide. So I would say entrapped in the rock above, it's mainly methane and carbon dioxide. And then with that sweeping of the air that we were talking about here, with the sweeping of the air through this area, we're picking up a lot of nitrogen. And when we pull on these to kind of keep that methane away from these guys underground, we're getting a lot of nitrogen and oxygen into those holes. Yeah. So how often is it happening? Not very often. So there are 550 active mines in the United States. Only 2.4% of them capture methane. The majority of them are destroying it. Like a few are recycling it. The majority of the recycling that's happening is for like on-site compression. There's only, and then of the abandoned mines, I pulled something from MSHA's database that said 30,000 abandoned mines. I'm sure there are more, right? But since they started registering them, there's only 0.1% of those 30,000 that are capturing. But what's up?
Do you know the ones that are the 0.1%?
Yes.
You know them by name.
Yes, and we'll get to some of them in PA later.
When you say destruction,
Just flaring.
okay.
Yeah. So this destruction is an increasing trend because in 2009, the California Air Resource Board said, hey, we need a carbon offset protocol. And one of the things that we're going to do in this carbon offset protocol is, sorry, I'm moving around a lot. One of the things that we're going to do is allow the destruction of this methane to qualify for carbon offsets in that market. And so we saw an increase there. Before 2009 and in the 90s, there was, and let me skip forward. In the 90s, there was like 15 projects that were put in place for beneficial end use and injection into pipelines. On active mines, there were power generation, there were thermal uses of this gas. So the reason that happened in the early 2000s was there was a Section 29 federal tax credit for alternative energy. There were really high gas prices. It was like the peak oil scare. Everyone thought, oh, this is the end of like production, and gas prices went through the roof, right? So there were a bunch of projects, and then so that was on the left-hand side, the lighter colors. On the darker colors, that's what exists today. So today there are only 3 unactive mines in the United States, 3 RMG use projects in the United States that are being injected into a pipeline. One is our operation in Virginia, which is a massive operation. We also capture from 6 abandoned mines in Virginia. So to put this into context, the amount of methane that we're capturing from this one operation in Virginia is enough to power 1 million homes electricity for 1 year. 1 million homes for 1 year. That's how much gas we're capturing. To put it in the context of greenhouse gas and kind of global warming perspective, it would be 5 million metric tons of carbon dioxide equivalent a year. That is the equivalent of a brand new forest the size of the state of Massachusetts. That's how much methane is currently being vented to atmosphere at this one mine that we're taking out of the atmosphere and we're putting into beneficial use, and we're avoiding all of those emissions to atmosphere, and we're able to power a bunch of homes. About 20% of that gas comes from abandoned mines. There are 6 abandoned mines that we capture from in Virginia. So about 20% of this impact and the amount of energy that we're producing is coming from abandoned mines. We do have the ability to do it in Pennsylvania, and I'm going to talk a little bit about that. But this process that we do is really similar to, maybe you've heard of landfill or dairy or swine farm, renewable natural gas. This is a really similar product because it's typically waste, which is going to atmosphere. We process it, we clean it up, and then we bring it to market. These guys have gotten a lot of federal support for their process. This process is very rare, and we don't get a lot of federal support. And that's something that I've been working on over the past 4 years, is to try to draw the parallels. If this stuff is being vented to atmosphere and it's being cleaned up and used and it gets federal funds, then why shouldn't we apply the same logic to this? Yes? Yeah, it is political, and the reason is, okay, so this is where the sources of coal mine methane are, right? There's really only 4 or 5 states in Appalachia that contribute to the greenhouse gas impact, whereas the rest have, like Utah, Colorado, they've got a couple of programs. These states, they've got a couple of programs, but like California doesn't have any mines. Washington, Oregon, they don't have any mines. New York State, they don't have any mines. Who makes policy related to climate solutions? It's representatives from those states. And so those states don't have those problems. Everybody in the United States has a landfill, right? Everybody in the United States has a cow farm, and so they can relate to, this problem, and they can think about their constituents and say, oh, I can bring jobs back to my state, I can bring jobs back to my district, I can make investments in my district, but like we don't have that coalition. Think about it similar to like the Corn Belt, Iowa, Missouri. These states have a coalition for corn subsidies. In Appalachia, we don't have a coalition of representatives that are going out there and saying, hey, this is both a climate solution and an energy solution. They don't have like a big enough voice to make an impact, whereas the corn states certainly do. They have a very powerful lobby.
Do you know if AMR is ever considered like saying this is a hazard, like a priority 3 hazard because of the methane, as opposed to like if there's an AMD coming out of a mine, they're like it's an environmental issue. You know if anyone or OSMREs ever considered methane as an environmental issue?
I'm not aware of that policy, no. So back to this question of like flaring versus pipeline injection. So another reason why we saw this pivot away from beneficial use towards like decommissioning those facilities is a lot of these facilities that were in service switched over to just flaring because they were getting these incentives through the California Air Resource Board. They were able to get these carbon offsets. We went to California and said, hey, we'd like to qualify these projects that actually use that methane rather than just destroy it, rather than just wasting this energy resource as heat. We'd like to do something beneficial with it because we as a society, we consume more energy, right, than we can possibly get our hands on. So let's put it to use, and let's at the same time credit the environmental benefit. The flare project operators said, no, wait a minute, we can't have you guys doing that because that will oversupply the market, and then my flare projects aren't going to be profitable, and I'm going to not allow you into the market. So we were prohibited from entering the market. If we do nothing, the problem will get worse. There was a study that was performed by an international community of scientists, and they're projecting a 3 to 4 times increase by the end of the century on methane and abandoned mines in particular. So what's happening here is, as mining progresses, some mines in this area are becoming abandoned, and then they start contributing to this green wedge, right? So as time progresses, more active mines will become abandoned, and that green wedge gets larger.
Are you just talking about the underground coal mines?
That is the primary source. There are so on this graphic here, you can see there's surface mine circles as well. This is the size of each circle is the estimated size of the emissions associated with the mine. So surface mine methane is a lot more difficult to capture, right? Because you're spread out over such a large area. The only degasification capture technology that's been deployed and has registered for offsets, there was a Peabody project in Wyoming. This big old yellow circle right here. They registered what's referred to as pre-mine drainage, meaning they went out in advance of the mining, the surface mining, and they drained the methane from the coal seam. And then when the mining actually happened, there was less emissions. But yeah, that's the only method that I know of on surface mining to capture emissions. So we talked about that one. I talked a little bit about carbon credits. So while the beneficial use of mine methane is not recognized by California Air Resource Board, it is a valid carbon credit at the United Nations CDM, Vera Climate Action Reserve, and it was originally in like the Kyoto Protocol. The US EPA says the recovery and use is considered an emissions avoidance. That's on their website. ISCC is a European, Asian kind of standard setter. A lot of multinational corporates reference that coal mine methane is a waste product under ICC Plus, which is a voluntary protocol, meaning if you have a company based in Europe or Asia, you want to buy mine methane derived products because it's recognized in your protocol. Basically, you have goals to hit, and this is one of the recognized ways. I worked with the United States Department of Energy 2 years ago and came up with a score for coal mine methane, and that score was minus 7,000 pounds of carbon dioxide per megawatt hour. So if you use this methane and you feed it directly into a power plant, you actually have a net negative impact in terms of greenhouse gas because methane is 28 times more potent of a greenhouse gas over 100 years than carbon dioxide. So that conversion from methane to carbon dioxide actually is a climate benefit. At the same time, you get megawatt hours that can be used. So the United States Department of Energy recognized that benefit, and they included it in their life cycle assessment model. Go ahead. If we get I think, let me put it to you this way. A solar or wind project gets a certain dollar per megawatt hour of federal and state subsidies because it's net zero. If I were to make net zero power using a mixture of coal mine methane and natural gas, and I got that same subsidy, this would be profitable.
So what makes it not?
What makes it not is we don't get that same treatment today. It's not that life cycle assessment science is only recognized now by the United States Department of Energy, but it's not recognized here in the state. It's recognized in Europe, right, by ISCC. It's recognized in Asia, but so what I'm working on today, and what we've been doing a lot of advocacy for is taking that United States DOE model and then getting it into federal policy. We made an accomplishment in May where it was recognized by a provision called 45Z, which was an Inflation Reduction Act provision that was then enhanced by the One Big Beautiful Bill Act. That made a lot of projects profitable. And we're hoping to do more because I want to see this make hundreds of projects profitable. Right now, I would say there's probably a dozen that are profitable, but I think if we get, basically, if more programs recognize this number, we would have hundreds of projects.
So the reason it's better for the environment is you're taking CH4, you're burning it, and you're turning it into CO2, and it's 1 carbon for 1 carbon or whatever, right? So
it's methane at 28 times global warming impact, converting to CO2 at 1 time, right? So for every methane molecule in, you basically reduce the impact by 28 times, and you get but there's an efficiency factor, there's leakage rates upstream, so like it all nets out to basically a 7-to-1 ratio. So once you do all of the, and these guys at Argonne National Lab in Chicago, they are some of the smartest scientists that probably walk the earth. So they did all the math and they said, for basically you could have a mixture of 7 traditional conventional natural gas molecules and 1 coal mine methane molecule. If you combust those 8 molecules together, you get 1 megawatt of net zero power.
Right. So you get power plus you get carbon dioxide instead of methane. So
right.
So you make power and you get better results for the environment.
That's right.
Before you move on to this slide, I see the mention of it being included in Tier 1 under the Alternative Energy Portfolio Standard. So can you comment on that? And is that not now helping because Pennsylvania has already hit its mark?
Don't get me wrong, that is the lifeblood of our operation in Virginia. The only reason we're able to continue to do what we are doing today and have not switched to flaring is solely because of that program. It's enough to keep us in operation in what is one of the gassiest, one of the largest mine methane capture operations in the world. I think that operation that we have in Virginia is the largest waste methane capture operation in the world. That because we are in PJM in Virginia, Virginia's in PJM. Pennsylvania Tier 1 allows any PJM resource, and we actually we actually transport that up to a Pennsylvania power generation facility. So the electrons are actually being made in Pennsylvania, but it's a PJM resource. That was a restriction that the program had. Yeah.
And how would the update,
Press and Pacer. Press and Pacer would help. Press and Pacer would help, and we've had good conversations, I think, with some of the early concepts, but I wouldn't say that it's not like a deal breaker. Like I talked about how 45Z and this Argonne model, it went from, I would say that model turned like a dozen projects profitable. The Pennsylvania program and past press, it might turn like 5 projects profitable. So it's not like a massive impact. So I've really been focused on federal programs because they have the ability to switch it from, it could be game changer, from a dozen projects to hundreds of projects.
So with PJM, you're basically almost guaranteed that they're going to buy your power through that process.
Yeah, so they have an obligation. So that's a good question. So electrical generation suppliers have an obligation to purchase a certain percentage of their portfolio from a set resource pool. Other resources in the Tier 1 category include out-of-state solar and out-of-state wind. So it's interesting though, because like out-of-state solar and out-of-state wind, it's like a 0 pound of CO2 per megawatt hour resource, whereas what we're doing is a negative carbon intensity, but we're trading on par basically with a North Carolina wind project on a per megawatt hour basis, even though our climate impact is more. We're getting the same price despite our climate benefit being better.
My question was to, I just kind of keep going along here.
Yeah, just keep going, man.
So, when you're burning methane for fuel, as you say that you might, does the CO2 byproduct contribute to the possible emissions like rise?
Yes.
And how, if that is the case, do you plan to essentially try to limit that byproduct of CO2?
Good question. Yeah. So that CO2 gets netted out, right, of the number. So that minus 7,000 has like a plus 1,600 associated with the CO2 that's baked in. Like if you didn't net that out, it would have been minus 9,000. Does that make sense? So that it goes into the math. The other aspect is we have projects that I'll talk about later where they're actually turning this methane into a bioplastic. So there's no, it's like a different process, right? And so that methane actually gets converted into a plastic. I'll just keep moving forward here. So putting it into global context, the U.S. is actually a really minor source of coal mine methane. China is 76% of global coal mine methane emissions. Just think about like as an industrialized society where we've moved, like that area is producing a ton of coal, and they are not doing anything they're not doing much to mitigate their emissions. They're doing some things, but they're not having a massive impact. If we look at the federal level, this makes about 7 to 10% of the methane emissions in the United States come from these mines. Global Energy Monitor is a kind of think tank at the international level. They estimate that in the U.S., the mine methane emissions are 80 million metric tons carbon dioxide equivalent per year. To put 80 million metric tons carbon dioxide equivalent per year into context, if you planted a new forest the size of the state of Montana, that is how much carbon dioxide would be sucked in, right? That's the same climate impact as the amount of methane emissions from U.S. mines every year. We talked a little bit about where they are. Again, Appalachia is kind of the bullseye. Between Pennsylvania, West Virginia, Virginia, Alabama, 80% of mine methane comes from those 4 states alone. So now, this is why I'm here, to talk about Pennsylvania's abandoned mine methane opportunity. So over the past month, I took a deep dive into what abandoned mine methane opportunities there are in Pennsylvania. So I pulled down from MSHA database, I found around 942 mines. There was an analysis, a very thorough analysis performed in 2009, and they identified 66 mines that they found as good candidates for coal mine methane projects. Since that time, there have been around 50 mines that have been abandoned. There have also been 11 mines outside of all of those that were reporting emissions to EPA after 2011, but then did not report in the most recent year. So that, to me, indicates they were an active mine in 2011. They had a bunch of coal mine methane emissions. They ceased operations. They're now either inactive or abandoned, and they're not reporting those emissions to the EPA. They are in Pennsylvania. They're now approaching abandoned or are abandoned, and they would be good candidates. So let's take a deep dive into the 2009 analysis. So the 2009 analysis looked at the 66 mines in PA, and they found at the time of closure and abandonment, the total methane emissions were 12.1 million metric tons carbon dioxide equivalent per year at each given mine. Then that analysis performed a decline curve and said, we are going to, for every year, we're going to estimate that a certain amount of those emissions are going to go away because there's less methane buildup, and the emissions tomorrow are not the same as the emissions today. It's kind of a stochastic empirical formula that they deploy. I think each mine is a little bit different, and the accuracy of that is a little bit suspect. Yeah, go ahead.
Sorry, just for clarification, are you using the same definition of abandoned as what we're pre-1977?
No.
That's what I thought. Okay,
So abandoned, the MSHA designation that we're using is it's abandoned according to MSHA, which is It's no longer in operation. The 1977, I would say that maybe like half of the mines in this 12.1 come from pre-77.
Most of the people in the room.
Okay, thanks.
We're coming from a SMACRA point of view.
Got it.
Pre-1977, abandoned means to us is pre-SMACRA. So,
Got it.
Yeah, it's just so.
Sorry about that. Yeah, so the analysis that I performed was using the MSHA designation. So then they had further reductions associated with water flooding. So if there's a bunch of water in the mine works that would suppress the amount of methane, they called around to a lot of the MSHA offices and they said, hey, what's going on at these 60 mines in terms of water flooding and sealing? And they were able to get estimates for roughly half of the 66 mines. There were 25 mines where they didn't know what was happening. And so what they did was they assumed the distribution of of the knowns applied to the unknown. And so they assumed 41% flooded, 49% sealed, and 10% vented. This is the abandoned mine methane numbers that are reported by Pennsylvania's Department of Environmental Protection in their inventory analysis every year. So PADEP publishes this. It's on their website. You can click on it. They publish the black line, which is on top. That black line is a accumulation of the 3 lines below, which is sealed, vented, and flooded. And again, the vented number is just lower because the number of mines they assume that are venting is less than 10%. And so this does exclude the 52 underground coal mines that have been abandoned since 2009. You can see here there's like a bump in 2009. This was the last mine that was added to their inventory analysis. So what's happening is active mines are becoming abandoned, but no one's taking a record of what their emissions are and adding it to the inventory analysis. There have been 52 that I know of that should be added. They're not being added. And then there's 11 that were reporting to the EPA as active mines, and they no longer are, and they're likely abandoned. Plus, there's 800 some odd other abandoned mines that were not, didn't have publicly available data by the people who performed the 2009 analysis. So, taking that all, okay, go ahead.
Real quick, did EGRIT, like the electronic greenhouse gas reporting tool for like active mines?
So I'm just focusing on abandoned. So the only active data that I include here was the 11 underground mines that were reporting to EPA after 2011 but didn't report in 2023. So the reporting requirement for coal mines started in 2011. Do we got to wrap up?
Yeah.
Okay. No, this was great.
You were about to give us your.
So this is the takeaway. This is my estimate. So we've got like the estimate from PA. This is my estimate. So PA's estimate's 1.3. I think I would adjust their model a little bit. I would include the reporting that was missing from the EPA, things that have happened since 2009. That would be that bit. And that's the 1.53. This is the EPA reporting. It's 0.34. The other 50, I estimate at 1.53. That gets you to a probable of 3.8. If you add in the other 800 mines that were missing from the original 2000 analysis, I think you would get up to somewhere around 10 million metric tons carbon dioxide equivalent per year from abandoned mines. This is the map of my estimate of where those are located. The size of each of those bubbles relates to the size of the emissions. The colors are related to the analysis. So the blue is the 2009 analysis that's used for the state inventory analysis. The green are those that were reporting to EPA and then stopped. And the red are the other 50 that closed since 2009. So that's basically the presentation. Yeah.
We can keep going because it is a break.
I mean,
next.
there's a break
Yeah.
for a few minutes and we could get a late start, but
Yeah.
yeah.
I think we all still have questions.
Yeah.
Go ahead.
Do you have any specific technology that you're looking at for trying to concentrate methane in these abandoned mines?
So our process includes a processing and inert removal. So there are like 3 or 4 different types of technology for that. There's nitrogen rejection units, amine systems. There's deox catalyst. There's membranes.
Now, that membrane, I was thinking,
Membranes are very energy intensive. So you've got to basically put a bunch of pressure on the inlet side, and then on the outlet side it gets down to a very low pressure, and you got to bring it back up again. So so there are 3 projects that I know of that happen in Pennsylvania. The Cambria 33 mine, which is now abandoned, had a project that did this. The Emerald mine, which is an inactive mine in Greene County, had it, and CNX had a project called Pine Bank, which was capturing from the Blacksville mine, which has like turned into Monongalia mine and had a portal in West Virginia, but sources of methane in Pennsylvania. So yeah, the Emerald mine used membrane technology. The Pine Bank facility used an amine system.
So then thinking about like the Surface Mines Control and Reclamation Act of 1977, all those that from our perspective are abandoned with no actual owner. Has the methane already been gassed off of all of those, or has any study been done?
Good question. I would say when you follow this when you follow this decline curve, like just with time, it's going to continuously get lower and lower throughout the years, right? My assessment of these mines was really, if they caught it in the 2009 analysis, there were certain mines that were post 1970, or sorry, pre 1970 closure that were analyzed in that 2009 analysis. Which of the blue are pre and post? I would have to go back into my spreadsheet to give you that. The problem is that they had to rely on MSHA data in order to come up with their analysis. So if MSHA said, hey, like how much methane emissions are you having, it was really a safety requirement. Yeah. And so that safety requirement started in a certain year. So the data associated with methane emissions prior to that safety requirement being put in place was never established. And I can tell you that going back today and doing like flyovers and trying to attribute the methane releases to a certain source is really difficult. Typically what happens is you have satellite imagery companies, they come in and they say, hey, look at these big plumes of methane. We've got a bunch of Marcellus and Utica shale gas operations happening here that are really leaky. Well, it's actually the legacy mines underneath are venting methane, and they're being misattributed.
Yeah, and that was part of my question then too, was how do you
attribute it?
Yeah, how do you attribute it, and then how do you incorporate it into like a reclamation plan? Because that's what we would all be concerned with or able to help you with, because we do the reclamation part of it, and how do you incorporate methane capture into a reclamation? Because from our perspective, what you're calling abandoned is they were active mines and there is somebody responsible for the reclamation. Right. So they're already cleaning it up and already responsible to do something with that methane release. So see how, I don't know if I'm articulating that correctly.
Yeah, I understand what you're saying. So that there's no legal requirement to capture the methane. Okay. There's a legal obligation to get the methane to the surface, but there are no requirements in the United States to cap the methane. Yeah. So I think the first step in assessing what to do with mine methane from an abandoned perspective is just to say how much is there, right? Quantifying the amount of emissions and then doing a feasibility assessment on a project, whether it be a flaring project for carbon offsets or doing something beneficial with it, like turning it into electricity. There are a lot of tools out there available through the EPA that help states or businesses do those economic evaluations. But yeah, quantifying just how much is there, it would be the first step, which can be done with like drone flyovers, or if you have somebody with the knowledge of where the vent shafts were, that's really where the methane is going to be concentrated. You go to the vent shaft, and that's where it's coming out, right?
For abandoned mines, a lot of times they're just collapsed portals or vertical openings.
Yeah.
Or, you know.
Yeah.
But
And you.
this
I
is
think
only
you-
like, this 9.7 is really just the active mine. I mean, the entire state, like
Yeah.
what 3/4 of being, I don't know how much of the state of it is undermined, but like if you actually look at how much of like abandoned undermined, it's huge.
Yeah, absolutely,
I don't think
absolutely.
that's even, you're not even touching it.
No, yeah. Like I said, I think that this one
Like,
captures it, right?
basically all undermined.
What I've basically assessed is this. This is what I've looked at, is this wedge. I have no idea what's going on with those 813.
Okay.
Yeah, very interesting. Really interesting.
And a part of it is there was no MSHA data, right? Like
Yeah.
the requirement to report methane didn't exist at that time.
Do you know how many megawatts that facility was that you said you had in Virginia? It's alright, you know.
It's like I want to say it is like 200. If you just burned it neat, it would be 200. We could get a gigawatt to net zero.
Thanks.
Will you be available for questions?
Absolutely.
Okay, yeah.
Happy to hang out. Thanks, everybody.